So it is time to talk about another equation used in chromatography. And this time it's going to be something called selectivity factor. So when we talk about something being selective, we're talking about maybe choosing between one of two or three or more things, right? That's what we really refer to as selective. If you're selective in life, then you're very selective and you pick out what you like the best. And chromatography systems kind of do the same thing. They're very selective when you give the chromatography system a mixture and it looks at the things that are inside of that mixture. It will focus on one or two things that it likes the best, and then all of the other stuff it maybe's okay with, but out of everything, one is typically going to behave the best out of all. And that's what we refer to when we talk about selectivity factor. Now, instead of the word factor, sometimes, or selectivity, sometimes you'll see the word separation. And, either one of these are okay to use. It refers to the same thing, selectivity factor or separation factor. Doesn't really matter. Okay, so for this example, we're going to talk about two species, and that's A and B. So these are going to be components inside of the mixture. And these components are basically going to be separated from each other in a chromatography system when we inject them into the machine. All right, so the selectivity or separation factor is going to have an abbreviation. I don't want to write this word every single time I got to use it. So instead, we use the symbol for alpha. And that's like the Jesus fish that sits over to the side. Okay? So selectivity factor, or alpha, is always, always, always greater than 1. So that means it's very important in how you plug these numbers into the actual equation that I'm getting ready to show you. All right, so selectivity factor, and I keep doing this. My fingers must be pen happy here, okay? All right, so selectivity factor, if we talk about the equation, is going to be alpha is equal to K prime B over K prime A. And we're always going to compare two adjacent peaks, really, when we do the selectivity factor. So over here to the side, I'm going to put two adjacent peaks almost every time that we use this equation. So adjacent, of course, means side by side. Okay, so we're looking at components that are side by side, and we're comparing basically the selectivity of this component inside of the chromatography system. So for example, if I draw the chromatograph down here at the bottom, I'm going to see one peak, and then I'm going to see another peak come up and come down. All right, so we're going to kind of label this as A, and we're going to label this as B. We now know what the K prime means. We've talked about this in previous videos. So if you don't remember what that means, I would say go back and make sure that you're okay with that concept, because this is the value that you need for the selectivity. So K prime B divided by K prime A, you should always get a number that's greater than 1, and that's basically going to give you a rough idea on how selective the chromatograph system can be between these two peaks. So if the column is selective, the peaks should be separated, right? We should see a baseline down here at the very bottom, and that should go all the way flat before our next component comes up, and in this case, that would be B for us. If I get a chromatogram and it looks like this, then this is A and this is B, and these two things are not really separated. So therefore, the column and the chromatograph instrument is not selective for those components. And that means that we've got some work to do in the field of chromatography in order to get these two things separated from each other. So if it's always greater than 1, of course, the higher the number, the better the separation or the selectivity factor. That's really what we're after here. So big numbers are going to be good for us when it concerns this type of equation. All right, so that's the selectivity factor, and that's one way that we can describe separation that's basically in a chromatograph system. So the second way that we can describe separation, and really the more common way that we can describe separation, is through this concept of resolution. How good are things resolute from each other? And when things are resolute, that means they're separated from each other. They kind of stand alone, right? They can hold their own ground, and that's what these peaks are doing. So here's a chromatogram, and on this chromatogram, there's all kinds of peaks. I mean, you can see them all the way down here to the right bottom side. And all of these peaks represent a different component. And there's some little bitty ones and then some really big ones. And those kinds of peaks we want to take a look at. So if I look at this SSS versus SOS, these two peaks we would know right off the bat. They look resolute. They look like they're separated enough where they are not interfering with each other. And sometimes we can look at these peaks and just know automatically, yes, this is separated. I don't need to do a calculation because it's clearly evident on the graph that they are nowhere near each other at all. So why waste my time, right? However, this SSL and the S00, these two peaks are side by side. Now, does it go all the way down to the baseline? And the answer is no. But are these two peaks separated enough? Because it does look like this peak comes down. And then that's when the second peak will come off. And are they separated enough? As long as the enough part is met, that's really all that we've got to worry about, because we know that things are not going to be perfect in the chromatography world. We know that peaks are going to look like this sometimes. So instead of doing guesswork and let somebody looking at it and say, yeah, that looks good enough to me, we actually have an equation that we can use to our advantage to prove if these two peaks are resolute enough. And that's what we call resolution, all right? How well are the peaks on the chromatogram separated from one another? Now, when we do this equation, we're going to get a number for the resolution, and we want greater than 1.5. Okay, that's the number that we're after. So when we plug these values into the equation and we solve for these answers, we'll write down just a random number and hopefully we'll get it correct. But what does that number mean? Well, the second part of those questions are going to follow up, and it's going to say, based on this value, are they separated enough? Yes or no? And you will circle yes every single time that these peaks have a resolution value greater than 1.5. All right? Okay, so there's a couple of ways that we can maybe increase resolution. If we get two peaks that are really close together and we want them further separated, what can we do in order for us to get a better resolution on our graph? Okay, so number one is we're going to slow down the flow rate sometimes. If you slow down the flow rate, you allow things to hang out in the column a little bit longer. And if they're hanging out in the column longer and they're taking their time to go through the column, then you're giving them more time to separate from each other, right? Sometimes they don't want to be rushed. Sometimes they just kind of want to hang out and chill for a little bit. And slowing down the flow rate will allow that to happen. A lot of people get this confused because they think that if they speed up the flow rate, you'll get better resolution. And that is not the case. Most of the time that will not work. And the reason is because you're pushing things through the column too fast, and you're not giving them time to separate from each other. You're not giving them time to feel comfortable in the environment that you're putting them in before you're rushing them out the other end of the column. So slow down the flow rate. That actually will help you more than speeding up the flow rate will almost every single time. The next one is change the mobile phase, for goodness sakes, right? So if you change the mobile phase and you throw in some pizza and some beer into the mix, then maybe those molecules will hang out a little bit longer and they'll behave a little bit better and they'll separate much easier from the non-beer drinkers to the beer drinkers. Who knows, right? The non-pizza eaters to the pizza eaters. So changing the mobile phase is going to be a very good option for you. And you can see how resolution will change accordingly. Sometimes it will come out better. Sometimes it will come out worse. But it's going to be a trial and error most of the time when you do these things. The next thing is that you can do a change of the stationary phase. Changing the stationary phase, that's pretty easy because the only thing that means is you change your column. So take the current column out, put a new column in, and that column will maybe have a different stationary phase on the inside. Different types of apartments, different types of hangouts, different types of bars that these molecules can hang out in as they travel through the column. And if you change the stationary phase, sometimes resolution will improve, sometimes resolution will not improve, and it will get worse. Again, it's trial and error for the most part, but these are kind of the order of the steps that you want to go in. Take the path of least resistance first, slow down the flow rate, then change the mobile phase, then change the stationary phase. And then if all else fails, and time is not really a big concern with you, then choose a longer column, right? If you choose a longer column, you're giving these components a longer amount of time to stay in the column and separate from each other. And sometimes this improves your resolution. The drawback here is that those longer columns will always increase your retention time every single time, no matter what you do. So longer column is going to be a longer path that these molecules have to travel in as you push them through. And if you gradually change the mobile phase or gradually change the stationary phase, you can improve the resolution. But with longer columns, you're getting longer flow paths, which means a longer retention time every time. So maybe your retention times go from 4 minutes to 40 minutes. That's something that you don't know until you actually run it and see how it happens and behaves. All right, so we need to talk about the equation for the resolution. And this equation, again, is something that I'm always going to give you. This will always be on a test for your reference. Whenever you decide that you need it, it will be there for you.